Hi, welcome to the 19th annual Christmas tree lecture, and maybe the first one that ever started on time. Nice to see lots of old friends here today, and I also see my friend Joyce sitting in the front row, who actually makes these webcasts possible. So I'm glad to see. If you haven't seen one of these before, the idea is, why did I start this 19 years ago? And that is because one of the most important things for computer scientists is the study of trees. Trees arise everywhere in our field, and so I figured, okay, every year I would tell something about the most cool thing I learned about trees during the year. And I have plenty of things stacked up for future years, but this year actually I had a little bit of trouble coming up with a title, because my first two things that I had saved for backup turned out that, although they were beautiful, I didn't think I could present them. They take a lot of detailed understanding. But then I come across this beautiful connection between planar graphs and ternary trees, which is not only, I think, very profound mathematically, but it turns out that I believe most of you will actually understand it, or at least if you watch the webcast again, you'll understand it. So it's pretty rare to find something new that is still not that far away from basic principles, but I do believe it's new, and actually some of this are things that I did this morning, but a lot of it I did last week or Thanksgiving weekend, and so it turned out to be a really rich area where it's always fun for a lecturer to speak when he has something interesting to say, and that's what I'm looking forward to tonight. Okay, so now stop me if you have a question, something that isn't clear. If you stop me too often, I'll get upset. But better to err on the side of understanding or not, because I do think it's not only great stuff, but also something I want you to get. So I start out this with an article from a journal that came out. Actually, this work goes back a little more than 15 years to the middle of the 90s, and some people in Florence and Bordeaux. Can we zoom in on this a little bit so you can just see the title? So Del Lungo del Ristoro Pinot wrote this paper called "Left Ternary Trees and Non-Separable Rooted Planar Maps." I just happened to stumble across it while I was looking on a completely different topic of satisfiability this year, because some of these same authors worked on that, and I saw it in their Vita. Okay, so the more I looked at this, the more I loved it, and so I'll try to explain the whole point. But basically, these guys started out, and they invented a new class of ternary trees. Now, ternary trees are something that I think deserve maybe a renaissance. But computer science, we usually use binary trees, which means that it consists of nodes where you have a root node, and then every node can have a left child and or a right child, or neither. In fact, the root doesn't have to be there either. But anyway, in binary trees you have left and right. But with ternary trees you have left, middle, and right. So here's an example ternary tree where the root has a middle child and a right child, but no left child. And then here the right child, in turn, has a left child, but no middle. And this guy has left and right. Okay, and then we stop. I just want to make an example out of it. Actually, there's some nice data structures based on ternary trees for searching. John Bentley had one, but I'm not going to go into that. But first, I can write down the number of ternary trees. If there are 0 nodes, there's 1 ternary tree. If there's 1 node, there's 1. If there's 2 nodes, there are how many possibilities? 3, right? Because there's a root, and then you have 3. Okay, so there's 3. And then if you go on to the next one, you find there are 12 ways to get 3 nodes, 55, 273. And you can always, once you got this many numbers, you can always find it on the online encyclopedia of integer sequences and carry it on. This happens to be, I wrote down somewhere what sequence number it is, but anyway, it goes on. Now, I'm going to go actually with the one more, 7752. Now, so that's the number of ternary trees, but these guys, in Florence and Bordeaux, came up with an interesting idea. They said, let's give every node a rank, and we start out with 0 at the root, and then the left child gets a rank 1 less than you. Your middle child gets the same rank as you. The right child gets higher rank. So this node gets rank 0. This one gets rank 1. Okay. Now this one going to the left gets rank 0, and then this one has -1, and this one has +1. Okay. So we can assign a rank to all these guys, and it's sort of the x-coordinate on the graph if you're plotting this. Although actually you can get situations where where there'll be a 0 and a 1 here, and these will be crossing over. It doesn't make a really beautiful diagram if these lines cross over, but you'd have interference, several nodes at the same level of the tree having the same rank, but it didn't happen in my example. Okay, but anyway, these guys said, what happens if we restrict ourselves to the case where I have to, in honor of history, actually, I have to say these guys actually went the other way. They gave it they gave this guy a -1 and this guy a +1. I don't know why. It confused me when I was reading the paper, so I decided, to change it. Well, now, if you look at the title of their paper, they call them left ternary trees. Okay. Now, our alumni are always complaining, and people in the press are always complaining about the liberal tendencies of university professors. So I want to, somebody has to right the balance a little bit. So I decided I'd switch everything over and move things that that lean to the right. So I changed their convention here. Okay, but now they had this idea that they'll say, well, let's look at the ternary trees that all the ranks are non-negative. And so, this one then just doesn't qualify. It's got this -1 guy in there. Okay, so now they call it left ternary trees, but anyway, other people, other researchers picked up the idea and have another name, and I like the other name better, so I call it skew ternary trees. And skew ternary tree is a ternary tree in which all ranks are greater than or equal 0, and the root is always 0, so you can't. That's the best inequality you can have there. Okay, so now they found out how many skew ternary trees there were, and it turns out it's this. What do you think? Skew ternary tree with 2 nodes. has to be 2 because you can't go to the left of the root, okay? And so on. So you get this table of numbers, and it goes on 22. It's interesting. You see 22 and 55. Could that be a coincidence? 91. If you're into factorization, you happen to realize that, you know, there's factor 13 here. Okay, 408, 1938. Now, when I saw this, I knew that this problem had my name on it because this is the year I was born. So it, you know, I had to, you know, it was sort of destined to give this lecture. Now, well, they noticed that, in fact, you know, 2 is 2/3 of 3, 6 is 2/4 of 12, 22 is 2/5 of 55, 91 is 2/6 of 273, and so on. All right. So, this amazed them, and they wrote a computer program, a very clever method. But anyway, and they let it run for a while, up to 30 nodes, and sure enough, it was checking out that it was always 2 over n plus 1 times the other number, or something like that. 2 over, except in the very first case. The very first case should have come out of 2 here, but well, experimental error. So, now. And then they went on to give a complicated proof of it, where they took all the ones that aren't skew and they converted them and then subtracted out other things and so on. Well, what I found at Thanksgiving was an extremely easy way to see why this is true, and so that's the first thing I want to show you today. So although my talk is called Planar Graphs and Ternary Trees, I'm going to start out with ternary trees, and I'm going to get to planar graphs later. Okay, so here's the idea. We start out, it's an idea that I thought of while reading an unpublished note by a man named Gilles Schaeffer, who's at Polytechnic in Paris. So here was my example, and now I do something that I almost always do with binary trees, and that is draw in the leaves where there's no child. I actually put something in here which I'm going to call a bud. Maybe I should do it anyway. So I draw in a bud between all the places where there were chance to have kids, but they haven't been born yet. Okay, so all right. Now, this in the case of a binary tree, I get in what's called an extended binary tree, and then I used an idea that I got from John Conway taught me this about 20 years ago, that actually even with binary trees, I should put a bud up here at the root too. Roots, actually they don't do this, but mathematically this makes it nice, because now every node is connected to 4 other nodes. There's one from above, the parent, or in the case of the root, it's the root bud, and the 3 potential children. Okay, so this makes it a graph in which every circle node here has exactly 4 neighbors, and every bud has exactly 1 neighbor. Okay, in fact that's true also at the in the case where there's no nodes at all. When there's no nodes at all, we start out with 2 buds that are connected to each other, so each one has 1 neighbor. Okay, so in general, if there are n nodes, which are the circles, then we have 2n plus 2 buds. It turns out it's easy to show this. Add one more node and you add 2 more buds. So it works even when n equals 0. Okay, so now what I do here then is I now have I now have 2n plus 2 ways to to make a ternary tree out of this, because I can take any of these buds and I can hold it up and I can let everything else go by gravity. Well, I still preserve the embedding in the plane. So I can start at this one and make it, or I can start here and I can dangle, it'll be a ternary tree this way. So no matter which one of these buds I start with, I could make it the root bud and I could dangle everything else coming down below it, and I'd get another ternary tree, right? Okay, now what I noticed is the following thing. I imagine an ant that crawls along the edge of this, okay? The ant's name is Alice. So Alice is the ant, and she starts out, and let me do it here at this, and she has a little counter which I'm gonna draw by straight line. But anyway, she starts out with a count of -2. It'll be clear why that's true in the first place. And then -1, 0, 1, +1, +2, and now she is going to do the following little game. Let's see. It'd be better if I actually numbered the buds. I'm going to number the buds 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's 14 buds. 1, 2, 3, 4, 5, 6. That's checks out. Okay, I haven't missed any. And I'm also going to put letters in the nodes. So I'll call this A, B, C, D, E, F. It gets a little messy here. But I want to show you what Alice is doing. So she starts out, and let's say she starts at the beginning, but she could start at any place, but let's start at the beginning. So she sees a bud as she crawls along the outside. And so when she sees a bud, she moves up 1, going from -2 to -1. Okay. Then what's the next thing she sees? She sees bud 1. But I have to tell you, she doesn't see nodes, but she sees branches between nodes. This is not a branch between nodes. This is a node to a bud. But between A and B, it's a branch between nodes. So I'm going to have, and the branch has 2 sides to it. And so there are n-1 branches between nodes, because there are n nodes and there's node cycles. And there's 2 n-2 arcs, which are each branch has 2 sides. Alice sees it, coming on this side, and then Alice is going to see it again coming the other side. So you watch what she does, and it'll be clear. So she comes along here and she sees 1, then she sees A to B, and so she goes down. That's her rule. She goes up on a bud and down on an arc. Now next she comes to 2, and then 3 and 4 actually. And so 3 is here, 4 is here, and then she's going to see BA, and that's going to bring her down here, BA. Okay, so next AC and CD. She's not going to see very many buds for a while here. Looks kind of bad. Here's DE, and she's down here, back where she started at -2. Now she sees 5, which takes her up, and 6 and 7. Okay, we're going up. Then comes ED. I hope I didn't screw this up. And then comes 8. Look, plan ahead here, Don. 8. Now, I should make an intentional error here and see if anybody catches it, but instead I'm going to just say DF. And then F, yeah, but I think I screwed up. Well, we'll see what, I'll patch it in a minute. Unfortunately, this is being recorded for posterity. Too bad. 8. Wait, I already did 8. Then I have DF. So E day. Okay, so then I got F, which is no DF. So this is 9, and then 10 and 11. Okay. And then F D, and then DC coming in here, and then 12, 13. Yeah, I did screw up because I'm supposed to come out with +2 at the end. Now, why am I supposed to come out with +2? Well, you see, there are 2n plus 2 buds, so there's that many plus steps. There's 2n minus 2 arcs, which is that many. That should be that many minus steps. So the pluses outnumber the minus by 4. So I should have gotten up from -2 to +2. So let's see. I didn't get all the arcs. 1, 2, 3, 4, 5, 6, 7, 8, 9 arcs. Somebody didn't get matched. So A, B, B, A, C. What happened to CA? Aha! I missed CA coming in here. No, wait. That's at the end. So I'm still okay. Oh, okay. Well, all right, no problem. Now, let me. Okay, but now let me show you why Alice thinks this is great. Namely, I can assign ranks to all the buds and all the nodes. Okay. So I assign a rank of 0 to, do I have another color pen here? I don't know. Okay. So, okay, anyway, we got 0 to this root bud, and I got 0 here. So this is -1. I'm going to just put a dot over it. This is 0 coming here. There's going to be -1 here, -2 on this, on these, sorry, 0, going back to 0 and +1 again. And C is going to get a 1. D is going to get a 0, E is going to get a -1, and this leaf down here is going to be a -2, this bud, I mean, and 6 is going to be a -1, and so on. So if you look at the diagram, you'll see that this rule actually corresponds to the rule of the ranks. Bud number 0 has, well, that's another experimental error. It says -2, but it's actually 0. Now, but bud number 1 has rank -1, that's correct. And then bud number 2 has rank -1. And you'll find that every bud here has the, as Alice is passing a bud, the number she had is exactly the rank that we had before, all right? So now, here we have a situation then that she's gone up from -2 to +2, and whenever there's a bud, whenever there's a node, the nodes don't appear here, only the arcs between nodes. But you can figure out what the rank of A is, for example, because you look at A B B A, and A B comes down here from 0 to -1. BA comes from +2 to +1. It always turns out that there's one slot in between the left parenthesis and the right parenthesis. You know, the AC and CA are going to be are going to also, this one is 2 steps higher than that guy. It's like the parentheses in German. In German text, people write like this in German, and so these little brackets here are sort of bracketing off little subtrees. When you see the arc, when she sees the arc first time and second time, she's gained 2 in the meanwhile, going below here. So I can tell what the rank of every node is also, and so it turned out that it's a skew ternary tree only if you never come back down to -2. here, because if you never have another bud of -2, then you're not going to get, only -2 is the root bud, then you're never going to have a node at rank -1. So in other words, the number of skew ternary trees are the number of paths that Alice can see that never hit the bottom line again. But now notice what happens if she keeps walking. She goes around again. Then she's going to repeat this exact same pattern again. She's going to go, she's going to see 0 and then 1 and then AB, on and on, 2, 3, and so this will be an infinite thing that moves up 4 every time. So if you look at it, it turns out that there's got to be exactly 4 places where she sees that rank for the last time. And so there'll be 4 leaves that don't have a mate if you go to the right. So here this leaf is mated by this one. You just move to the right to hit something else. But then there are some that never get canceled again. And so 5 is one of these lucky leaves. 6 is another one, buds I mean, this was 9 actually. This guy, this is 10, this is 11. 12 is another one that I think is never going to be hit again. Yeah. So exactly 4 of these guys are going to survive in the sense that if I started out with leaf number 5 and I build a ternary tree by hanging down, it's going to be a skew ternary tree. Okay. So I have now actually written a program that you can find on the internet called Skew Ternary Calc, which does calculations on skew ternary trees. And as I was preparing this, I needed to do more and more larger trees, and I started writing many of these paths. And every once in a while I would screw up, and then that would give me bad data, and I would make bad conjectures. So I got this program and put it on the internet, and you can find it just by go to the Computer Musings webpage, and there's a link that'll point you how you can download the program, and it's what I call a literate program, which means I include documentation explaining it. And here's an example of a skew ternary tree that appears on the first page of the documentation, and so it shows pretty much what I did here. But can you zoom in a little bit more on this, please? Owen, just to see the left hand. Yeah, good. So in little red here you can see the ranks, and then I made the leaves looking a little bit nicer, and so I did what I showed you, and then here's what happens if I take the buds and put them around a circle, and then you can still see where the nodes appear in the middle. Now here's a picture that shows the way buds get paired to each other, except that 4 are left in this example. And so 0 doesn't get mapped to anything. And here's Alice's walk. With showing what I did, but here we have a skew ternary tree, so it never comes back to -2 again. And if you start at 4, it's another one of these that's unmatched. Okay, so here's a very simple proof. Instead of proving that 2 out of every n+1 ternary trees is a skew ternary tree, I proved that 4 out of every 2n+2 is a skew ternary tree, and that's just as good. Okay, now, so you take that particular example. This was the one we had before, and then but now start at bud number 4 instead of 0, and you get another case now where it comes -2 to +2, and so it becomes a skew ternary tree, and we have these different things. So now, what do the trees look like? Well, I call the initial one T, and then I call this one T plus, and this is T double plus, T triple plus. So these are 4 associated skew ternary trees, and then quadruple plus would take us back to the same one again. Now, what I found out to my great surprise was that there actually are some strange affinities between these four trees, and I still haven't psyched it all out. But there's something there that I think is going to be important. I don't know if they'll be teaching it in high school in 10 years, but anyway, it's got me excited. So. Next part of the anyway, this proves the conjecture very simply that there's a relation between these numbers and these numbers. Four out of every 2n plus 2 of these cyclically related ternary trees have the skew property. Now, next, planar graphs. Okay, so more precisely, I'm going to talk about rooted planar graphs. So I'll stick to nice pictures here somewhere. I hope I have. By the way, this is a computer program, but you also has pictures. You can read the program. It's mostly explained, but anyway, it does all the parts. You can input a tree and it calculates the related trees. Okay, so now anyway. Here's a planar graph. And let's zoom in on this little guy here. Okay, so this is a very simple planar graph. It has 4 vertices, 1, 2, 3, 4. It has 6 edges, A, B, C, D, E, F, and then it has what they call faces, which are the things between the regions that it's a planar graph. It divides into regions, and so we have region Roman numeral 1, 2, 3, and 4, and so this is of course very very basic. I find that though when I read books on graph theory, the stuff on planar graphs usually confuse me because I'm much better at algebra and combinatorics than I am at geometry and visualizing stuff. But so I have to work on it very slowly, and the books almost never treat the degenerate cases very well. I mean, even if I draw a ternary tree, I've drawn this in the plane. And so it's I mean these vertices are make a planar graph, but the representations that people have for these things usually they don't people who write those papers aren't interested in the simple cases, which seem to be more common. So anyway, but there's a beautiful data structure for representing planar graphs with all of the degeneracy cases and everything handled in an incredibly beautiful way, published by Leo Gibas and George Stolfi, Transactions on Graphics, 1985. And here's what they do. And so inside the computer, to represent this graph, they have a data structure they call a quad-edge data structure. And it's certainly, I think it's the winning data structure by far. I looked at Wikipedia, they have some competitors, but quad-edge is really the winner. And I think I have, in my program here, I have a better implementation of quad-edge than I had seen before. But anyway, you can take a look at it. So here's what it is. The data structure represents the edges, and so A, B, C, D, E, and F are represented here by A, B, C, D, E, and F in circles, and then the vertices are indicated by loops of okay. Well, I call these okay, I have these little dots here that I call pips, and a vertex is a circle of pips, and a face is a circle of pips, and every edge is attached to 4 pips. And so think about a planar graph. An edge does 4 things. It separates the left face. An edge has a left face and a right face, and it has a vertex ahead of it and a vertex behind it. And so these are the 4 pips. So each edge here has a pip coming out to this vertex 1. It has a pip coming out. I call it pip number 2. Pip number 3 goes to face phase 4, which is a cycle of pips. Pip number 1 goes to this outer face here, which is a cycle of pips, and pip number 0 is 4 here. So that says that edge A has this outer face 1, Roman 1 on the right, Roman 4 on the left, and 1 this way and 4 that way. Okay, so the quad edge data structure is every edge has 4 pointers associated with it, then the vertices and the faces are implicit as cycles within these pointers. So in a sense, it's all edges, and the other things are secondary effects. But I'll show you the computer representation, which makes this really cool. But notice one other thing, that going counterclockwise, I do have some leftist tendencies. So I go counterclockwise around every vertex and counterclockwise around every face, except the outer face. The outer face has to go clockwise, and that's just to make everything balanced. Because if you look at it, it's got to be that way. And because when you're drawing on the plane, it's really drawing on the surface of a sphere. It's the best way to look at it, and not on a plane. So and so the outer face is somehow on the other side of the sphere, and that's why it's going clockwise the other way. Anyway, as I said, I'm not great at geometry, but it's true. Now, inside the machine, each one of these connections between an edge and a pip is simply a pointer. So so I have a permutation of pips, and here's zoom in just on this one line, Owen, so we can read this. I hope everybody, a little more zoom, please. Kind of zoom here. Okay, here we go. Oh, that's a little bit too much. Okay, now, all right. So I have a permutation I call it alpha that corresponds to that picture I showed you a minute ago. Alpha is a computer representation of this diagram, and what it says is A2, D2, C2, B2. Sounds like a character in Star Wars. It says that these are 4 pips coming out of edges A, D, C, and B that form a cycle. So A2. So if you look at pip A2, which is this guy, it goes to this pip, which is D2, and this one C2, and this one B2. Whoa, I'm in the wrong place. Okay, so here's A2, D2, C2, B2, going around this way. Okay, so but inside the computer, I just have I don't know, 20 memory locations, and there's a pointer from location A2 to location D2. Every edge has exactly 4 locations associated with it, and those are just pointers which form a permutation. One entry in your array is pointing to you, and you're pointing to somebody else, and that forms a group of cycles. So it turns out then that it's very simple to manipulate this inside the machine, and it's a very efficient representation. And there's and it turns out you can do everything you want to do on planar graphs with just one primitive operation, which is called splice. And the splice is something, and so this is explained in the program. I don't have time to go into detail, but basically, a splice says change 2 pairs of pointers, swap 2 pairs of pointers, so I don't have time to explain the details, but the main thing is if you ever play with permutations inside the machine, you know what happens if you swap. For example, if I swap pointer. The pointer that's in location D2 with a pointer that's in location F0 or something like that. If D2 and F0 are in the same cycle, it breaks the cycle into 2 parts. if D2 and F2 are in different cycles, it joins the two cycles together. And this is something that we use all the time when we operate on data structures. We're making two cycles into one or one cycle into two. And in this case, the even-numbered pips, 0 and 2, are always to vertices. The odd-numbered pips, 1 and 3, are always faces. And so in this case, I can see that I have 1, 2, 3, 4 vertices, because that's how many cycles there are. And then there's a cycle, there's also 4 cycles, there's 4 faces in this side. So a cycle, goes A1 to F1 to E3 to D3 and back to A1 again. So anyway, for me, this was great because instead of having these pictures where I can always get confused and have a little trouble drawing them, I'm just dealing with permutations which are easy for the computer to manipulate, and the computer can make an important change just by swapping different pointers with each other. All right. So now, anyway, I wanted to implement this for the following reason. You might ask, why did these guys take a look at this? Why do they spend so much time or in inventing quaternary trees and coming up with these numbers? And the reason is that there was a very great paper by Bill Tutt, which is celebrating its 50th anniversary this year, where he showed that these numbers are the number of planar graphs of a certain kind. So I'm going to tell you what that certain kind is, but he enumerated planar graphs of many different kinds in his paper, and so nobody believed that you could actually count planar graphs very easily. They just seemed pretty complicated. But he figured out that actually there was a way to deal with it, and so. His paper was in a Canadian Journal of Math, volume 15, 1963, page 526 to 545. One of the great papers of all time, always worth rereading. No, wait, I'm sorry. This is 249. His student wrote a sequel on those pages. Here's 249 to 271. This is the one. Okay, so now, so what kind of planar graphs does this enumerate? And the answer is that it enumerates the building blocks of which planar graphs are constructed, called the blocks of a graph. And so I want to explain this is something that applies to any graph, but especially has a special theory in the case of a planar graph. So building blocks of planar graph. So any connected graph with multiple edges can be put together by combining what they call blocks. Other people call them biconnected components. Other people call them non-separable graphs. And you attach these blocks by things that are called articulation points or cut vertices. And the idea is you have a block, and another block is hooked onto it just in one place, and there's no cycles between these blocks. So the blocks tend to have a tree-like connections to each other. Okay, and the points at which they are attached are actually, the block can also be just like this, called a bridge or an isthmus. Okay, and the points where these are attached are called articulation points. And anyway, so in order to study a complicated graph, it suffices to study blocks and then the way that blocks are fit together in a tree-like manner. Okay, so we have the blocks of a planar graph, These are things that don't have any, you can't cut them apart by, at a single vertex. Now, then he also says, let's take one of the edges and put an arrow in it. Let's see, I have some simpler. I have a simpler one here. So let's take. So here's a planar graph that doesn't have any cut vertices. So it makes a block, and I put an arrow in it, and I call this a root. And so the arrow gives an orientation and designates one of the edges of the graph, and also assigns a direction to it. So this is called a rooted non-separable planar graph. Now I'm adding another condition also, that I'm going to throw away trivial cases where you have only 0 vertices or 1 vertex. And so I have what I'm in the notes here, I call it a rooted non-trivial biconnected planar map. But that's such a mouthful. In the notes I call it RNBPM. But in this lecture I don't even want to say that, so I'm going to call it an R map. Now, we want to count R maps. We want to count rooted, non-trivial, biconnected planar maps. You know, how many ways are there to make a planar graph that you can't divide and it has a root in it? How many different ways are there? The answer was actually 1, 2, 6, 22, 71, 91, 408, and so on. So Tut proved this very indirectly, by something having nothing to do with actually graph properties, but by an algebraic technique. He came up with this sequence of numbers, and then some people, actually Professor Corey in Bordeaux, said, well, you know, there must be a way to do this combinatorially and find a reason for these numbers, so he asked people to look at it, and that's why these Italians came up with the idea of skew ternary trees, because they thought, okay, now that we have this, we know how many skew ternary trees there are, maybe we can associate one skew ternary tree with every rooted, R map. Okay. Now, so in order to let's try to get the concept here. Let's figure out how many R maps there are with a small number of edges. So first of all, if there's only one edge, it's pretty clear that it's just the root edge. You have only one possibility. Now, what about if there's a root edge and one other? The other one has to go this way, because otherwise we'd cut it off. It wouldn't make a block. So can any but there's supposed to be two of them. Two ways to do it with two edges. Can anybody tell me what they are? So I got to add two edges to this diagram, but I'm not allowed to have a cut vertex. Okay. Nobody can figure it out.
The other one goes down?
What? I can't hear.
The other one would have the edge.
Oh, well, anyway, one answer is to make a triangle, okay? So, because it has three edges nicely, and I can't break it off and disconnect it in two parts. But there's one other that has three edges.
The one with the arrow in the middle?
Yeah.
Yeah.
Okay. All right. Now, but that brings up an interesting thing. That is, when I'm counting these things, I'm counting the number of ways to draw them on a surface of a sphere, And so if I call these A, R, and B, for example, then that would be exactly the same as if I put B up here and R at the bottom, because on the surface of a sphere, you could slide this like a rubber band around the bottom, and it would come out on the top. And so you consider that this drawing of a planar graph is the same as this drawing of a planar graph. So when I talk about a planar map, I'm saying how many ways are there to put it on the surface of the sphere and decompose the surface of a sphere into regions that have the topology about left and right that's preserved. Certainly, if I drew the picture this way, you would say this diagram is like this one, or if I put if I put some wiggles in the lines, that doesn't matter. The main thing is, though, is the ordering of faces. At every vertex, you see the edges in a certain order, and every face you see the edges in a certain order. Yeah.
Why is A different from B?
I'm just labeling it here now.
Aren't they the same?
They could be the same if I didn't put the labels, but if you do put the labels on, the reason I'm putting it on is because I want to show you something else. This is equal to this, but ARB is not the same decomposition of a sphere as BRA. Actually, there's a difference, because if you look at it, you're seeing B, then R, then A at this vertex that coming into the root. But in this one, you're seeing A, then R, then B. That's a different cyclic permutation. So you can't go from this on a sphere to the other one. I can go from this one to this one by sliding B around the back. Maybe not understand now why. Maybe some of you share with me this idea of that algebra is a little more comfortable when you're counting things than geometry, because you can make slips like this. But you have to understand what we're counting here. We're counting different ways to subdivide the surface of a sphere according to the rules of what's different. And what's different is that you have to be able to convert one into the other by smooth things without only stretching, doing things that are topologically smooth. So this is reflection is not the same as something that I can do in a sphere. So now, but back to my question of so anyway, this one is the same as this one, and I wouldn't have to put the A's and B's in there at all if I'm not labeling things. Now. But I do want to fix the idea. So let's see if people come up with the 6 examples that have 4 edges. And according to Tut, there are 6. Okay, so you got to add 3 edges to each of these diagrams. And one of the great advantages of being able to count them with trees instead of with these drawings is because trees are much safer. You don't make with drawings. It's easy to do hand waving and get lost and forget to count something or miss something. But trees are pretty easy. You can enumerate skew ternary trees. Are pretty easy to find out that there are exactly 6 skew ternary trees with 3 nodes. So. I'll give you one. It's a square, or a quadrilateral. So that's one example. Now, are there any examples that have only 2 vertices? Okay, yeah. Just add 3 edges like this. That does it. Okay. Now, what do you think then? Are there any more that have just 2 vertices? I don't think so. So now, What about 3 vertices then? So that means I have one more vertex here. Okay. What?
Triangle with the friend.
Triangle, like this, and then you can arc going down here?
Sure.
Okay, now, by the way, I'm going to put the arc here. I'm going to put it up here instead of down below. The reason is that it turns out to be a good idea to normalize it so that the right of the root edge is the exterior face. So you're looking out at the face that's sort of at infinity on the goes to the other side of the sphere from you. So I'll put it up here instead of below. But I could have put it below, but I'm going to keep this on the exterior. Okay.
Triangles and and one on the either side.
Okay. So I can go like this, and the other one is also actually different. Mm-hmm. Right. Okay. So now there's one more. According to Tut. I mean, I'm not sure what it's going to be. What do you have? Okay. Well, we're running out of time. But so the answer is, you also have this guy. All right. It's probably what you said. All right. So there are 6, right? Now. And so the problem was faced is, okay, now find 6 ternary, skew ternary trees that correspond to this, right? And so this was a big conjecture going around the middle 90s, and 2 groups found solutions to it, and the one is the paper I showed you before. The other is something I have in the program and I've implemented, but I'm not going to go into it now. And so here it is. This one turns out to be, and actually I'm going to put labels on it so that you can actually see what's going on. In fact, that's one of the keys. Whenever I find a one-to-one correspondence, even if the one-to-one correspondence is between unlabeled things, I always like to put labels on and see what happens, because you want to know what parts of the construction are being affected by what parts of the correspondent. Okay, so this one, it turns out to be A, B, C, like this. This one is, this one I called CAB. I should put the, this is CBA. The correspondence actually, gives you the 3 nodes, and then you can see how those nodes got into the correspondence by, and it turns out that this edge is C sort of gave us this node. So this one is going to be A, B, C, and this one is A, C, B. This is A, C, B, and okay, I'm almost done here. B, C, A comes down to A, B, C. And last is A, where is it? B, put B here actually, and A here, and C, and that's A, B, C. These are the 6 ternary trees and the corresponding chart. Now the correspondence has some geometric significance. The first thing is, if you look at the nodes of rank 0, those are the nodes. Those correspond to edges that touch the root. This guy at the root. So here's A is here it touches A. Here it touches A, B, C. Here it touches A and C. These are the two. These are the nodes of rank 0 in clockwise order. Here's A and C. Here's just A, and here's A and B. So you see the nodes that turn out to have rank 0 are correspond to the degree of this node here. Then the nodes on the outer face, on the outer face, A, B, C here is it's just C, here it's C, C, B. You get those by looking at the buds of rank 0, not the nodes of rank 0, but the buds of rank 0. So there's a bud of rank 0 here, and here's a bud of rank 0, but a bud of no, sorry, the bud of rank. Bud of ranks, the bud below the lowest node of rank 0, and then all future buds of rank 0. So if I don't count this one because it's this one gets swamped by this guy, but if there had been any branches out here, they would have counted. So these buds qualify here, and so the fact that A and B are on the outer edge, and here it's B and C, corresponds to this bud and this bud. This bud's for you. Okay, so their correspondence. I can't go into detail, but fortunately, it's extremely easy to. I can describe enough of it so that you get the flavor of it, and I can at least show you the program for it, which is let's see. Owen, can you show my program on that? So it starts here. This is and goes here, and that's and it's just a few lines of code. In fact, I wrote them last night and debugged them this morning. So, okay, now, so what the thing is, it ties into ties in beautifully to the to this idea that we had about dangling the buds and finding the skew trees. And the way that Alice crawls along all ties in with this, and so so here it is. First of all, they build all R maps, but by a recursive by simple binary operation on maps, and I illustrate it here. And it's a join operation, which I call a join with a C over it, like this bow tie operator. So here I have an R map which has say three other edges on the boundary. Here's another R map, and inside, shaded in green, is internal structure that doesn't matter. After we're going to connect these things up. And they can be arbitrarily complex inside, but we're going to build up all R maps from the most trivial R map, which is a single root edge, by this one binary operation, and the binary operation consists of three steps. The left operand has two roots. It's doubly rooted. We have a root edge, and we also choose any other edge on the boundary, on the exterior cycle, on the exterior face. And so then, but the one on the right is singly rooted. And here's what you do. You attach the two guys together at the point of this second root here. So the second root points to that vertex. So I've taken this guy and I've hooked the incoming edge of its root to the second root of A. Right, and then after I've done that, I erase the root edge of B of this guy, and I kind of open up Pandora's box and let some of this green stuff maybe escape out. But then I close it off with the new edge C, which kind of takes the place of that old root edge, and so I add one. So anyway, this is a construction by which it's not hard to see that you can take any R map, any large R map, and you can divide it up into smaller R maps. Why is that? Well, you just take your big R map, and you look at the edge right after the root, And then then if you take that away, you'll see what happens. And it turns out that there's either going to be a cut vertex here or not. And if there's not, that just means that that B has turned out to be a triviality. It turned out to be just a single edge. So this one construction explains everything. So in order to find corresponding ternary tree, we just have to have a way to build up a ternary tree by means of a bow tie operation on ternary trees. That you can take two ternary trees, put them together, and that gives you another skewed ternary tree. And then to go backwards, you have to go from that other one and figure out which two you build it out of. You have to have also the concept of double rooting in here. And the answer is that you, let's see, I don't know, I guess I don't have a diagram, but let's see, did I show, do I have a picture here? No, I didn't write the picture. Okay, so I'll show you the picture. So here's what happens. I have a skewed ternary tree. Let's take one of the examples I had on the other page, because it takes less time to draw. So I look at the tree, and I find the last node of rank 0. In this case, it's A. And so since it has rank 0, and it's the last node of rank 0, it does not have a left child. It can't have a left child, it won't be skew anymore. It can't have a middle child because it won't be the last node of rank 0. So it has, at most, a right subtree. So I can cut it up here into two parts. And that corresponds to the two parts of my bow tie operation. Now, if this part is empty tree, then it turns out to be the simple case of the bow tie operation where the guy on the right is empty. But in general, this will be, I can, in general, I get a tree here, and what I do is if I call that tree R for the right subtree of the guy I detached, I can go from R to R minus to B, which is another skewed ternary tree, but it has the property that if I place it in rank 1, it won't. I'll be able to find it again. So let's see. I got my tree here, and I'm going along, and Alice's path is going up. Sorry, not that way. It was going up and down and up and down, and it finds finally the last node of rank 0. That means it finds the last bud of rank -1. This is -1 here. It's going up to +2. And so after this, the line is clear, and I've identified the last node of rank 0. That's essentially this place here where I drew a cut. So now everything else appears up here, and this subtree. In that case, BC is going to be something that's bracketed by an AB and a BA in my diagram, and I can take a look at that subtree, and it's going to stay above this line -1. So now if I move from this to the -1, it shifts everything down 1, and that means that it'll never get above. Yeah, I mean, it'll never get down to -2 because it never gets down to -1. So by putting R to R minus, I'm taking R into another tree that I can recover, and I can put it down here. So anyway, looking at that'll tell me. going the other direction, I can take I can take a big one and I can figure out which tree this came from. If I'm trying to build the tree from the diagram, I take my tree for the first case and my tree for the second case, and I go and I call this R and change this to R plus. But by putting this in R plus, it'll be something that I'll be able to find later on when I'm going back the other way. So it's all a little hard to explain to people the first time. I have to admit I was working on it for more than a week. But the point is that it's actually easy for a computer to understand and actually a very short program. And now I got to come to the punchline, because I started playing with this and I found out that it has magical properties. The most amazing was this. I start out with a given tree. Well, let's see. I don't have my diagram here, but okay. So I start out with an example tree. And I did make that picture, I'm sure. That gives the. Wait a minute. I didn't put it in the write-up. Okay. All right. So I made the illustration, but I forgot to put it in the notes. I'll fix that tomorrow. If you start out with this this example tree for this, here's a skew ternary tree, so it corresponds to a certain R map, and so I have T, and then I had T plus, T double plus, and T triple plus. And each of these has an R map, which I call M, M plus, M double plus, and M triple plus. So according to this computer, according to this correspondence rule, which is actually very easy to program and to implement with the quad edge data structure, I get these four maps. And then, so I noticed that actually these maps were all duals of each other. So the dual of a planar graph is what you get when you consider the faces to be vertices and the vertices to be faces. So if you go back to my picture of a planar graph, where we had it represented, let's see, quad edge data structure. Okay, so yeah, here. Suppose I suppose I take this exact same picture, but I change but I rotate at every edge. I rotate the edge 90 degrees, and so what used to be pip number 0 is now pip number 1, and so on. Then this A is now pointing at between where it was previously having one vertex to the north and one to the south and one face east and the west. Now you went by 90 degrees, and so now you've got a vertex on your right-hand side and a face in front of you and a face behind you, and then you go another 90 degrees and you're seeing the the original vertices but in the other direction. And so what turned out, and this is just amazing, you take your skew ternary tree and then you hang it off of the second free bud, and you get the graph that corresponds to reversing the arrow of the root edge. So the external face turned out to be the internal face, and if this is T, then T plus is no, I think T plus is B. I don't remember. I think it's A, B, C, or something like this. And then the T double plus is CBA. And T triple plus, anyway, what happens is if you take this graph and you dualize it by changing every edge and turn 90 degrees, it corresponds to the operation on skew ternary trees, evidently, that has this magical property. Now, this I think is a miracle. I noticed it. I don't see how to prove it. I'm not sure I'll have time to figure out, spend any more time on it. That's what I wrote this program so that now you can play with it and look at, you can look at dozens of examples. You can put in any ternary tree you want to. You can modify the tree a little bit and see what does this do to the R map that you get. And in every case I tried, there was this connection between the dual of a planar map and the related trees. So this suggests that it must be true. I mean, God wouldn't want something to be true in 60 small cases and to fail in some other case. It just it's too clean a thing. But so that means that that much more must be true that I haven't figured out yet. I need a stronger induction hypothesis to prove, why is this happening? So it might be, for example, that there's that there's a bug named Bob that knows how to crawl along a R map, and the way he crawls along has maybe he does some kind of a depth first search of this R map, and he encounters the edges in some way that matches what Alice was doing with her crawling around the skew planar. Planar trees. There's got to be some, some reason why this is happening, I imagine there might be some kind of an algorithm that puts something on a stack, and the rank of a node in the quaternary tree corresponds to the number of things you've got on the stack or something like that. But then this algorithm will have to explain why. It'll have to be symmetrical somehow. No, an edge in a node in a ternary tree has 4 neighbors. It has something coming from top and 3 things coming out. An edge in this quad edge data structure has 4 pips going on, and but that doesn't seem to. I mean, that's okay. There might be related, but the relation is very obscure to me because in a tree there's no cycles, but in the planar graph there's cycles all over the place. So I have a feeling that this might well reveal some new properties of planar graphs that have eluded, even though this is one of the most worked out parts of graph theory, might have eluded people for years. And so I'm hoping that somebody's going to take a look, run examples with my program, and also, of course, there's a great opportunity to make an app where you can manipulate these things and click on things, move this around and see what and see what, or change the ternary tree and see what happens to the graph. So, 45 years ago, I came up with an idea about a one-to-one correspondence between what's called Young tableaus and matrices of zeros and ones, or matrices of non-negative integers, and it turned out that this is now known as the RSK algorithm, where K stands for Knuth, and many people have made a career out of studying the ramifications of this. Well, now this potential thing in the correspondence of these 3 authors, I call it the DDP correspondence because the author's names. So by putting letters on the on the ternary trees and seeing this fact that there are actually 4 related ones, which seems to be a new fact, was one step. But the fact that then it goes on and matches the duality of planar graphs, this is mind-blowing. It means that there must be something else going on, and I suspect then that there's going to be some theory, some other things coming out of this. So I want to urge everyone to drop whatever they're doing and work on this. Well, I have to go back to the art of computer programming. Okay. So, all right. So I'm a bit over time. But I do have time for questions. I answered all the questions. Yeah, there's a question. Bill.
This is an obvious remark. Way back at the beginning, before you added the ranks and the skewing,
Yeah.
You had these ternary trees. You can make the nodes carbons and the buds hydrogens, and then you've got the alkanes.
Excuse me, I could make the nodes what?
You can make the nodes carbons and the buds hydrogens, and now you've got the alkanes. In other words, the
Octanes.
No, alkanes.
Alkanes.
Yeah, yeah. Okay, so it's
okay.
unsaturated. Yeah, saturated non-cyclic hydrogen.
I see. So
Okay, and they've been studied to death, so you might check with those people to see if they figured out what adding that rank would
you
do.
think there are skew alkanes? Maybe not non-alcoholic alkanes?
CnH2n plus 2.
Yeah. Okay. Okay. Very good. Well, with that arcane remark, I'm just pronouncing it Japanese way. I wish everyone a Merry Christmas. Thank you. If you're into factorization, you happen to realize that, there's factor 13 here. Okay, 408, 1938. Now, when I saw this, I knew that this problem had my name on it because this is the year I was born. So it had to. I had to. It was sort of destined to give this lecture. Now, well, they noticed that, in fact, 2 is 2/3 of 3, 6 is 2/4 of 12, 22 is 2/5 of 55, 91 is 2/6 of 273, and so on. All right. So, this amazed them, and they wrote a computer program, a very clever method. But anyway, and they let it run for a while up to 30 nodes, and sure enough, it was checking out that it was always 2 over n plus 1 times the other number, or something like that. 2 over, except in the very first case. The very first case should have come out of 2 here, but well, experimental error. So, now. And then they went on to give a complicated proof of it, where they took all the ones that aren't skew and they converted them and then subtracted out other things and so on. Well, what I found at Thanksgiving was an extremely easy way to see why this is true, and so that's the first thing I want to show you today. So although my talk is called Planar Graphs and Ternary Trees, I'm going to start out with ternary trees, and I'm going to get to planar graphs later. Okay, so here's the idea. We start out, an idea that I thought of while reading an unpublished note by a man named Gilles Schaeffer, who's at Polytechnic in Paris. So here was my example, and now I do something that I almost always do with binary trees, and that is drawing the leaves where there's no child. I actually put something in here which I'm going to call a bud. Maybe I should do it anyway. At the same level of the tree, having the same rank, but it didn't happen in my example. Okay, but anyway, these guys said, what happens if we restrict ourselves to the case where I have to, in honor of history, actually, I have to say these guys actually went the other way. They gave it they gave this guy a -1 and this guy a +1. I don't know why. You know, it confused me when I was reading the paper, so I decided, you know, to change it. Well, now, if you look at the title of their paper, they call them left ternary trees. Okay. Now, our alumni are always complaining, and people in the press are always complaining about the liberal tendencies of university professors. You know, so I want to, you know, somebody has to right the balance a little bit. So I decided I'd switch everything over and move things that, you know, that lean to the right. So I changed their convention here. Okay, but now they had this idea that they'll say, well, let's look at the ternary trees or all the ranks are non-negative. And so, you know, this one then just doesn't qualify. It's got this -1 guy in there. Okay, so now they call it left ternary trees, but anyway, other people, other researchers picked up the idea and have another name, and I like the other name better, so call it skew ternary trees. And skew ternary tree is a ternary tree in which all ranks are greater than or equal 0, and the root is always 0, so you can't, you know, that's the best inequality you can have there. Okay, so now they found out how many skew ternary trees there were, and it turns out it's this. What do you think? Skew ternary tree with 2 nodes. Has to be 2 because you can't go to the left of the root, okay? And so on. So you get this table of numbers, and it goes on 22. It's interesting. You see 22 and 55. Could that be a coincidence? 91. Often I'll get upset, but you know, better to err on the side of understanding or not, because I do think it's not only great stuff, but also something I want you to get. So I start out this with an article from the journal that came out. Actually, this work goes back a little more than 15 years to the middle of the 90s, and some people in Florence and Bordeaux. Can we zoom in on this a little bit so you can just see the title? So Del Lungo del Ristoro Pinot wrote this paper called "Left Ternary Trees and Non-Separable Rooted Planar Maps." I just happened to stumble across it while I was looking on a completely different topic of satisfiability this year, because some of these same authors worked on that, and I saw it in their Vita. Okay, so the more I looked at this, the more I loved it, and so I'll try to explain the whole point. But basically, these guys started out and they invented a new class of ternary trees. Now, ternary trees are something that I think deserve maybe a renaissance. But computer science, we usually use binary trees, which means that it consists of nodes where you have a root node, and then every node can have a left child and or a right child or neither. In fact, the root doesn't have to be there either. But anyway, in binary trees you have left and right. But with ternary trees you have left, middle, and right. So here's an example ternary tree where the root has a middle child and a right child, but no left child. And then here the right child, in turn, has a left child, but no middle. And this guy has left and right. Okay, and then we stop. I just want to make an example out of it. Actually, there's some nice data structures based on ternary trees for searching. John Bentley had one, but I'm not going to go into that. But first, I can write down the number of ternary trees. If there are 0 nodes, there's 1 ternary tree. If there's 1 node, there's 1. If there's 2 nodes, there are how many possibilities? 3, right? Because there's a root, and then you have 3. Okay, so there's 3. And then if you go on to the next one, you find there are 12 ways to get 3 nodes, 55, 273. And you can always, once you got this many numbers, you can always find it on the online encyclopedia of integer sequences and carry it on. This happens to be, I wrote down somewhere what sequence number it is, but anyway, it goes on. Now, I'm going to go actually with the one more, 7752. Now, so that's the number of ternary trees, but these guys, in Florence and Bordeaux, came up with an interesting idea. They said, let's give every node a rank, and we start out with 0 at the root, and then the left child gets a rank 1 less than you. Your middle child gets the same rank as you. The right child gets higher rank. So this node gets rank 0. This one gets rank 1. Okay. Now this one going to the left gets rank 0, and then this one has -1, and this one has +1. Okay. So we can assign a rank to all these guys, and it's sort of the x-coordinate on the graph if you're plotting this. Although actually you can get situations where where there'll be a 0 and a 1 here, and these will be crossing over. It doesn't make a really beautiful diagram if these lines cross over, but you'd have interference several nodes. Hi, welcome to the 19th annual Christmas tree lecture, and maybe the first one that ever started on time. Nice to see lots of old friends here today, and I also see my friend Joyce sitting in the front row, who actually makes these webcasts possible. So I'm glad to see. Yeah. If you haven't seen one of these before, the idea is, why did I start this 19 years ago? And that is because one of the most important things for computer scientists is the study of trees. Trees arise everywhere in our field, and so I figured, okay, every year I would tell something about the most cool thing I learned about trees during the year. And I have plenty of things stacked up for future years, but this year actually I had a little bit of trouble coming up with a title, because my first two things that I had saved for backup turned out that, although they were beautiful, I didn't think I could present them. They take a lot of detailed understanding. But then I come across this beautiful connection between planar graphs and ternary trees, which is not only, I think, very profound mathematically, but it turns out that I believe most of you will actually understand it, or at least if you watch the webcast again, you'll understand it. So it's pretty rare to find something new that is still not that far away from basic principles. But I do believe it's new, and actually some of this are things that I did this morning, but a lot of it I did last week or Thanksgiving weekend, and so it turned out to be a really rich area where it's always fun for a lecturer to speak when he has something interesting to say, and that's why I'm looking forward to it tonight. Okay, so now stop me if you have a question, something that isn't clear. If you stop me too